Interconverting pH and pOH. So luckily we have a very useful expression derived from the ionic product for water, which allows us to interconvert the concentration of pH and pOH. So the idea is that water autoionizes. So if you have a solution of water, water and water. Well, water is amphiprotic. That means it can act as both a Bronsted-Lowry acid and a Bronsted-Lowry base. So one of those water molecules can donate a proton to the other one. So if we imagine that first water donates a proton, what do you have left after it's donated a proton? Well, you have OH minus, so that's the conjugate base of water. And then what do you get if you accept a proton as a water molecule? Well, it's going to be H3O plus, the hydronium ion, so that will be the conjugate acid of water. So this is an expression for the autoionization of water, and we can write an equilibrium constant expression, remembering the rules of heterogeneous equilibria. Well, water is a liquid, so doesn't have a concentration, right? Because it's a pure liquid. So it wouldn't appear in the equilibrium constant expression. So our equilibrium constant expression is just going to be the concentration of hydroxide, times the concentration of hydronium is all that's going to appear in the equilibrium constant expression. And equilibrium constants will, just equal K. K equals this, and we give the subscript for the acid dissociation constant Ka to say, hey, it's an acid, and we give a subscript for the base dissociation constant Kb, saying, oh, hey, it's just a base dissociating whatever. We do the same thing for water. We give it a K subscript W to say it's the ionic product for water, okay? So when we write P to get pOH or pH, P just means negative log. So pH is the negative log of the concentration of hydronium. pOH is the negative log of the concentration of hydroxide. The value for Kw, in case you're curious, is 1 times 10 to the power of minus 14. Oh, whoops, I meant to make that box bigger. Whatever, we're not using this one. So if we do P to everything in this equation, we get pKw, and then we get that pKw, if we do our rearranging log laws, is the sum of pOH plus, I can't find my plus pH, and minus log of 1 times 10 to the power of minus 14 is just 14. That's kind of the point of doing this minus log scale, to get everything in kinds of nicer numbers. So we can use this to calculate pH if we only have pOH, or vice versa, pOH if we have pH, etc. Be very useful later on when you're working out ice tables to work out the concentration of hydroxide generated by a weak base, but you've been asked to calculate the pH of the solution. Okay, so we can rearrange. We're asked to calculate pOH, so let's just rearrange this expression. pOH is pKw minus pH, and we know the value of pKw is 14. So this is just going to be 14 minus 5.7. And now, because 14 is the ionic product for water, you're going to kind of treat that like any kind of constant, where you treat it as have like infinite sig figs. So it's not going to affect the amount of sig figs you give your answer to, essentially. You're only going to just match the sig figs that your pH or your pOH was given to. So 14 minus 5.7 gives me a pOH of 8.3. So pH plus pOH of a solution should always add up to 14, and that will help you work out what you don't know.